These figures outline the deadliest offshore oil disaster in history. By the summer of 1988, the Piper Alpha platform was producing 10% of the United Kingdom's total oil output. On the night of July 6th, 167 men died there. A single piece of paper, a suspended work permit for PSV 504, sat unread in the safety office. It documented the removal of a critical pressure safety valve from a condensate pump, a detail that the night shift operators had no way of knowing as they began their shift. The destruction of Piper Alpha is a textbook study in systemic drift. When an organization normalizes small departures from safety protocols, those adaptations compound. A complex system slowly and quietly drifts toward catastrophic failure. To understand how a billion-dollar asset can be lost in under 30 minutes, we must look past the fire itself. We must forensically deconstruct the official Cullen inquiry to see how latent architectural flaws intersected with routine procedural decay. This photograph shows Piper Alpha in its operational prime. It was a massive industrial footprint standing on 4 steel legs in 470 feet of water, dominating its sector of the North Sea. The platform was designed in the mid-1970s with a strict set of engineering parameters. Its pipe tolerances, its layout, and its safety infrastructure were mathematically rated exclusively to handle the extraction and processing of crude oil. During the 1980s, the platform's purpose expanded. Occidental Petroleum retrofitted Piper Alpha to handle high-pressure gas, bolting heavy new compression and condensate modules directly onto the existing legacy layout. Retrofitting volatile chemical processes onto legacy architecture introduces mismatched physical tolerances. Routine, daily operations often mask these structural vulnerabilities until the system encounters an extreme event. This 3D wireframe schematic maps Piper Alpha's topside. 4 production modules shared tight space with the wellhead, control room, and production deck. Module C, handling gas compression, sat directly beneath the living quarters. Its physical firewalls were original oil-era infrastructure, never upgraded during the gas retrofit. Those legacy walls were rated for thermal load, meaning they could resist a prolonged oil fire. They were unrated for the violent overpressure wave of a high-pressure hydrocarbon gas explosion. By processing high-pressure gas adjacent to the living quarters, behind insufficient blast walls, Piper Alpha harbored a severe architectural condition. A major gas leak was structurally impossible to contain. On July 6th, day-shift maintenance crews initiated 2 simultaneous jobs on condensate pump A. They opened Permit 1 for a planned pump overfall and Permit 2 to remove a pressure safety valve, PSV 504, for recertification. This elevation diagram shows the physical state of the equipment. Because the safety valve was removed, the open pipework 12 meters above the deck was temporarily sealed with a blind flange. The crew left that flange only hand-tight, and from floor level near Pump A, it was completely out of sight. When work was suspended for the night, the documentation was physically separated. Permit 1, detailing the pump overhaul, was left in a box right next to Pump A. Permit 2, stating that the safety valve was missing, was filed away in the distant safety office. At 1800, the day shift handed over to the night shift. The Cullen inquiry cited a total lack of spoken communication regarding the missing valve. Verbal handovers had been abandoned to avoid the friction of daily work, leaving the system to rely entirely on paperwork. When a safety system relies on disparate paperwork rather than active communication, missing information defaults to assumed safety. The incoming shift began their work under the assumption that the system was secure. At 21:45, condensate pump B tripped and went offline. Within minutes, gas alarms started blaring across Module C as the gas processing train began backing up. The night shift operators faced an urgent decision. They could shut the entire process down, incurring a massive loss of production, or they could press the start button on the standby unit, Pump A. Acute operational pressure forces a spike in cognitive load, narrowing human focus.
With alarms screaming, operators sought the fastest logical solution to stabilize the rig. They checked the permit board and found the overhaul permit, which stated that work hadn't yet begun. They concluded the pump was safe to run. They never saw the second permit filed in the safety office. Human operators facing severe time constraints will trust the data immediately in front of them. They are unlikely to halt a billion-dollar facility to verify a piece of paper that might or might not exist in another office. Pump A was started, and high-pressure condensate flowed into the pipework. The hand-tightened flange 12 meters above the deck immediately began to leak. A vapor cloud of light hydrocarbons rapidly filled Module C, found a spark, and ignited. This image captures the immediate aftermath of that blast at 21:59. The explosion was survivable, but the pressure wave instantly destroyed the unrated legacy firewalls. Burning oil cascaded into the lower modules, fracturing a crude oil line and sparking a massive pool fire. A redundant safety failure followed. The platform's automated diesel firewater pumps never activated. To protect divers working near the water intake, the pumps were habitually left on manual override. Despite an audit demanding an end to this habit, the pumps remained on manual, unreachable through the smoke and flames. This map of the North Sea floor shows the external escalation. At 22:20, a high-pressure riser pipeline bringing gas from the neighboring Tartan platform ruptured, flooding the Piper Alpha fire with 3 tons of gas every second. Even with the flames visible on the horizon, Tartan continued to pump. The control room operators there lacked the procedural authority to shut down a major export pipeline without explicit permission from a central authority on shore. With internal power lost, automated safety systems overridden, and the offshore installation manager paralyzed by shock, the Cullen inquiry found that the platform was technically decapitated. Inside the accommodation block, the men off shift had gathered according to protocol. They sat waiting for evacuation orders that never came. Because the block was not designed to be smoke-proof, dense, toxic fumes from the burning oil seeped into the ventilation paths. This is the MSV Tharos, a massive, heavily equipped standby rescue vessel positioned less than a mile away. It carried a hospital and a hydraulic gangway designed to reach a stricken rig. But the radiant heat from the continuous gas fireballs was so extreme that deploying the gangway was impossible. 167 men died. The vast majority were killed by smoke inhalation, sitting exactly where their training told them to sit, waiting for an instruction from a command center that had ceased to function. The platform burned for 3 weeks before the last of the pressurized gas vented and the fires died out, leaving only the charred, twisted legs of the rig in the water. In a decapitated system, rigid adherence to static emergency protocols transforms a refuge into a tomb. The men who stayed in the designated safe zones died. The majority of survivors were those who ignored protocol and jumped into the sea. 3 years before this disaster, an Occidental contractor died on Piper Alpha due to a nearly identical communication failure during a shift change. An investigation was held and recommendations were signed off as implemented, yet actual daily behavior on the rig never changed. Lord Cullen inquiry crystallized this failure in a single sentence. The safety policies and procedures were in place. The practice was different. That finding forced the creation of the 1992 safety case regime. Offshore operators could no longer assume compliance via internal checklists. They were legally required to proactively document and prove their specific hazard controls to independent regulators. Modern process safety is built on the memory of Piper Alpha, a reminder that safety requires a continuous, active defense against systemic drift, misplaced documentation, and hand-tightened flanges. If you found this forensic analysis useful, please consider subscribing to the channel. Thank you for watching.